All right, I guess we can start. Hello everyone, welcome to today's session. It's going to be a live soldering session. I'd like to welcome you all from our office in Amsterdam. So what we are going to do is to do a soldering session of the generic node that we released a couple of months ago. It's a completely source available design. You can check it out in our GitHub page. It's a double-sided board, so it's going to take a while to do the whole session, so it's going to be a long one, but please stick with it. I'll try to make it as entertaining and as informative as possible. So without further ado, let's get started. First, I would like to introduce you with the setup quickly. So we'll have a full overview here. We'll have a desktop view, we'll have a overhead view here, and a bit of an overall view. And let me switch to this cam. Okay, here we have a hot air station. We have a OT-ARC configurable power supply, battery profiler. We have a small soldering iron with the helping hands. We have a trusty reflow oven. So I'll talk a little bit about the soldering process, how we're going to do it. There are typically three types of soldering methods to do the SMD soldering. One is a hot plate. I have a hacked iron here, so I might also try to use this one. Or we can use the reflow oven, or just use the hot air station. Reflow oven usually gives the best result, so that's what we're going to use mainly. For those who don't know about the okay, let's switch to the workspace view. Okay, for those who don't know about the generic node, it's basically a very small device. It has multiple sensors on it. It has a buzzer, a user button, RGB LED, and we also have a, let me show like this. We also have a temperature humidity sensor, 3-degree of freedom accelerometer, secure element, and flash memory. It uses a latest STM32WL, the dual core version, and it can do 868 and 915 megahertz frequencies, and it has a extremely low power consumption. So we measured last time around 1.8 microamps in sleep mode, and it has a couple of user-friendly expansion options, like this is the programming board mainly, this is the GPIO, and we also have a quick stemma connector to add a sensor extension. Over the last couple of months, or actually a bit more than a year, we had a couple of versions. So this one you see, this was the first functional generic node prototype. And basically you see the evolution of the device. We had slight errors with the design, and as you can see, most people actually who saw the design, they really liked it because of its curvy layout. But from the back, we had battery connectors. So when the design error here was that when you attach the batteries, they would sometimes extend these clips too much and cause a So, sorry everyone, there was a drop in the stream. You know, it's a live stream. Whatever can go wrong will go wrong. Malcolm Murphy will get you. So please stick with us, because it's a live stream, many things can go wrong, and we'll try to fix the problems as we go. So where we left off, I was talking about this first version of the generic node. As I mentioned probably earlier, that so this was the first functional version of the generic node with all the same sensors and the same hardware, with the different curvy layout. And then we changed the design, changed the enclosure a little bit. Schematics stayed the same, but the layout was mainly a layout change. The problem with this design was that, you see the battery clips were too close because the enclosure that we were using was like too cramped for this to be used with two AA batteries. And when you stick the batteries in, the clips would extend and sometimes cause short circuit. So that wasn't ideal option, so that we ditched this design and then did more rectangular layout. It was even smaller than this. So as you can see, it has a couple of user-friendly pin headers on each side. It has a quick expansion port for I2C devices, and has a standard widely used JST input. We have a buck boost converter, so it can receive voltages, input voltage from 1.8 up to 5.5 volts. And it's at 3 volts input, it consumes around 1.8 microamps in sleep mode. And on the back side, we have a secure element here. We have a accelerometer, 3 degree of freedom. We have a temperature humidity sensor. We have 16 megabits of flash memory for data logging and for firmware over-the-air updates. And we also have a user button and RGB LED. This whole thing goes inside here in the watertight enclosure. As you can see, the holes are covered. This is a hole for the button and this is a hole for the RGB LED. There's actually another hole here, and that's for temperature humidity measurements, but that is also covered with the air permeable but waterproof mesh sticker. And this enables us to have a IP rating. It's not official, but that's what enclosure manufacturers claims to be IP65. So the generic node comes in this black box, black packaging, and we also have a black version we just made for trying different options. So this is the current version, this is the final version, and it comes with a shield on top. I just removed so that you can see it close up. Basically, this can do 868 and 915. It's with the software switching, and there's also option to add external antenna. And this was mainly these two were basically the same, schematics-wise, layout-wise. It's just that some couple of logo improvements and fixing the labels, things like that. So now I would like to go through the soldering process. As you've seen, generic node is a double-sided board. Here I have a basically a bare PCB. It's a double-sided board. It has a good mix of through-hole and SMD components, and also it's a 4-layer board, which is makes a bit of a challenge to do it live soldering on a dense board like this with some 80 components on it. But we'll try to do our best, and hopefully at the end we'll have a functional generic node. So here is our setup, and now I will also like to show you the workspace. Okay, we have sourced all the components. We have laid them out nicely according to the BOM list, and we have one part of each BOM listing. So as you can see, the components. This is a sticky paper. I don't know if the stream was dropped, so I don't know if I mentioned that. So we will actually So we have our stencils here. This is for the top side, this is for the bottom side. And we also have solder paste. This is from Chip Quick. You can see the part numbers. This one does not require refrigeration, but this one does. But it's already in room temperature. All right. So let me switch to the microscope so I can show you the PCBs better. So let's start soldering. I'm gonna use the matte black version anyways, because yeah, it looks nicer. And hey, what? Okay, it's matte black. That's the main reason. Okay, we also have a couple more bare PCBs, which we're going to use as a support. And then we'll use we'll start with the back side of the PCB. Then let me rearrange it a little bit. So I'll use the other empty PCBs as a side support. So this is how I usually do. Okay, once we have everything aligned, we take the stencil, we align on the components. Okay. The alignment must be as good as you can get. Then we'll have a really nice solder paste application. One trick I typically use is using these 1mm neodymium magnets. So if I spread them around like this, it will hold the PCB really firmly in place. Okay. Okay. So as you can see, the magnets are in place and PCBs are really firmly fixed. Then take our stencil, align it. I'll make a bit closer. I hope you can see it. All right, alignment is good. Then we take these strong magnets. Oh, it shifted a bit. All right. What it does, that the magnets make sure that the stencil doesn't move around when we apply the solder paste. We have a metal squeegee and we're going to use this. All right. So let's apply the paste. There are not many components on the back, so yeah, a little bit of paste would be enough. It's also actually a good idea to clean up any dust, small dust particles that might get in our way. Because we have very small laser cut openings, and then they will just go on the way of the solder balls. Okay, now we do the solder paste application. Doing this takes a bit more try and learning. The trick is to do it at one go. Don't do it several times, and then on the second go you do the cleanup. Okay, I'm gonna show you exactly how I do it. So we lay it down like this at around 45 degrees angle, and then we slowly apply, okay, a little bit left here, and then we do the cleanup. Okay, let's see how it turned out. Slowly lift this up. Let's have a closer look. Yeah, it's not perfect, but I think it will do the job. As you can see, I hope it's visible on the camera. Okay, we apply the solder paste to the back side, and we also will clean up the stencil in case we want to use it again. So I'm going to remove the stencil. Put this aside. Also clean up the squeegee. By the way, I'm using isopropyl alcohol. I have a spray bottle here. Okay, this looks good to me, so we can start picking and placing the components. this one aside. So let's switch the view to the laptop and go to the back side. Okay, we start with the capacitors. We have sourced them all. Now we're gonna place them one by one, starting with 100 nanofarad caps. Okay. Then we'll go to 10 microfarad, and then the resistors, then the couple of diodes, and the sensors. Just disregard the logos because they're also somehow included in the final BOM layout. So we have our 100 nanofarad caps, all 0402s are here. Sometimes I think I can do it under the microscope so that you can also see what is going on. Okay, let me try to do it under the microscope. Okay. Yeah, the solder paste is slightly shifted. And that means it might cause some short circuits. So, okay, no worries. What we can do, we can actually quickly clean this up and do another run of the solder paste application. So let me do that real quick. Okay, let's clean this up with the isopropyl alcohol. It's actually better to clean the PCBs up before applying the solder paste, then it removes all the contamination, and solder paste sticks to the PCB much better. Okay, now we have our empty PCB cleaned up. Now we're gonna bring back our paste application platform. Okay, let me clean the stencil again. Okay, it is clean. Even though we have here our strong magnets to hold them in place, sometimes when you apply the solder paste, the stencil might shift around a little bit. So in order to avoid that, we're also going to apply some tape. All right, let's use just a paper tape. Then we do the same process. Then we do the cleanup. Perfect. Now we very carefully remove the tape and also lift up the stencil. Perfect. Now we can just lift things up and have a closer look. Guess this is much better. Let's look under the microscope. So, yeah, still, as you can see, yeah, that will do the job. That's better than the previous run. All right, now we clean up the squeegee real quick, and also clean up the stencil. Then leave this aside. I'm gonna use my other tweezer. So, as you can see, we have a button here. We're gonna skip the button for now because it will go in our way when we do the double-sided soldering. We will do the button soldering at the end manually. So, as I mentioned earlier, we start with the capacitors. I'll quickly switch to the backside. Okay, here. Okay, you can see the red points where I need to install the caps one by one. I'll basically follow the same process. Switch back to view. All right. So, first one, 100 nanofarad. And okay, first one goes here. And the second one goes to here. Let me try to do a closer here. This should be better. Okay, another one, and that is for the accelerometer, which goes here. So if you just use one hand, you might have a shaky hand a bit, but if you use both hands, then that will stabilize the placement process, and you can just wiggle a little bit on top to make sure that sticks to the paste. So the paste will hold it on the PCB, and when we move it around, it won't fall off. Don't worry about the alignment if it's not perfect. The surface tension, when we do the reflow soldering, it will align all the components perfectly. Might be some tombstoning, but it's nothing we can fix with the hot air station. All right, the next one is also for the accelerometer, is this one. These are bypass caps, so decoupling caps. All right, that's good. Another one for the secure element. did 3. Actually, we did 4. There's one more left. And that is for the temperature and humidity sensor. As you can see, decoupling caps have to be physically placed next to the IC that they are decoupling, as close as possible to the VCC pin, and with a nice solid connection to the ground, so that there won't be any glitches in the VCC line when the sensor turns on and starts doing some measurements. Alright, that looks nice. I think the lighting, my hand gets in the way of light, but I hope you can see. Sorry, it's a bit hard to do the multitasking, but yeah, that looks good. And then alright, then we do the 10 microfarad, which is here. And that is a 0603 part. And that goes also for the accelerometer. Okay, done. Next. So next we do the resistors. So there will be 2 pull-up resistors, which are placed here for the I2C line, and those are 4.7K. So let me zoom it out a bit. Okay, resistors are here. I'm gonna pick 2 of them. Actually, I can bring the board closer, and we'll just place the component. This one. That's the second one. Nice. Okay, let me wiggle that cap a bit, right? Okay, that is done. Next. 330 ohms. Oh, okay, that's for the RGB LED. 330, that is here. One goes here. The other one, these are probably red and green colors, and the blue one will have slightly lower resistance because it needs more current. Yeah, the values might seem a bit low, but just so you know that the generic node is operating at 2.8 volts. So that's the main reason why we used lower value current limiting resistors. Okay, done. So now we have another 10K resistor for the flash memory. Okay, 10K is here. Probably a pull-up resistor for the chip select pin. Even though I designed the board, I don't remember all the nets and lines off the top of my head. All right. 10K placed. Next one is 1K. Okay. 1K. Here. Oh, actually, this is the red. Right. Next one, 100 ohms, and that is for, yeah, that's the EMI suppression resistor for the buzzer control pin. So it's 100R. As you can see, we have a couple of jumper joints. If you don't want to use the buzzer, but you want to keep using the GPIO for some other purposes like ADC and things like that, you can just cut them like here with maybe an X-Acto knife, and then you can start using that GPIO for something else. Okay, that's done. Next one. Oh, we are done with the passives, except the diodes. Okay, now we're going to place the RGB LED. Make sure that okay, it's focusing. Okay, make sure that the pin 1, there's a small notch on the top right hand side, goes here. Okay, that looks good. Maybe a little bit of tweak. Perfect. Then, I think as a background this works better. Okay. Next one is, oh, okay. So that's a really small Esd diode. By small, I mean that is the size, like it's barely even visible. It's to protect the button presses. And okay, let me just verify the polarity of this, because it's really hard to see. I'm using a small jewelry microscope like this. Okay, so the anode needs to be rotated like this. Then it goes like this. We're going to go through all of the component alignment under the microscope. Once I place all of them, then we can do small tweaks if they are misaligned. That's one disadvantage of having a black PCB, is that it's really hard to see traces and black components on it. But other than that, it looks really cool. Okay, next.
That looks indeed very cool, Orkhan. So during this live soldering stream, we're gonna invite some leaders in the industry to give a little bit of a comment on the challenges they see and the advice they have around the IoT solutions in building and being successful. So first here is Afzal. I'm gonna add you to this stage. Afzal, hi, can you hear me, Afzal?
Yeah, I can hear you. Can you hear me? Hello, hello.
Yeah,
I can hear.
perfect. You might want to turn off the live stream itself to make sure that there's no Can you hear me? Do you
I
have?
can hear you.
Can
Can
you
you?
check your internet connection? It looks a bit flaky at the moment.
I'm here. Can you hear me? Hello, hello.
Yeah, we
I'm
can hear
here.
you, so that's great.
Okay, great.
Hey, so Asal, can you maybe introduce yourself and tell me what great advice you have for 2022 if you're in IoT?
Yeah. So thanks for having me, by the way, Wieneke. So my name is Afzal Mangal. Amazing to be here. I work for Deutsche Telekom IoT. Some of you maybe know it as T-Mobile or T-Systems, but they both belong to Deutsche Telekom. Deutsche Telekom also has a separate IoT unit, and I created a corporate startup within Deutsche Telekom IoT, which is called IoTcreators.com. And we started this basically a couple of years ago because we saw the need to make mobile IoT access. And when I refer to mobile IoT access, I mean narrowband IoT and LTM. We saw the need to make it more accessible and more developer friendly, like what the Things Network is doing for developers. So that's what we're doing with IoTcreators.com. And this was kind of a spontaneous live session to me. Thanks for that, Wieneke. It's always nice to do such sessions. And my advice for 2022, and my assumption is that a lot of people here in the audience today are making their own IoT solutions and providing these solutions to others. My advice for 22 is basically never work for free. Because what I've seen in 21, I've seen a lot of IoT solution providers working for free. You know, there's always this big client, usually a telecom operator or a system integrator or an IT integrator or a consultancy who comes to you and asks the question like, hey, can you make this very cool sensor for me? Because I have a client and they have a potential for 10,000 or 20,000. So what I saw is that many of these IT providers were like, yeah, I'm going to invest in it. I'm going to invest all my time in it and I'm going to make a prototype. And what usually happens after a prototype, the customer will be very happy. And the integrator or the telecom operator, the guy who's in between you and the end customer, will usually offer like an end-to-end solution to the end customer. And what happens a lot that those big guys, those big companies, they make an offer of 100K for something that you can do for 15K. And you can guess what happens, right? Nothing will happen and innovation gets stuck. I've seen this many times in 21, but also in 20. And I really think it's time for you guys, for IoT solution providers, to stop investing your time in such free projects. That's my first advice. But maybe I
Great.
should stop talking right now and let Monica
Oh,
react.
no, yeah, there's a bit of a delay in this one. We're going to fix that soon. But yeah, really great. Just to summarize, don't do free POCs. Don't be starstruck by just let's say, the size of a customer, but be very critical. Okay, what's the solution? Where's the budget? Are the people that you're talking to making decisions, and then you do business. So yeah, that's great advice. So we'll put this down. We'll put everybody that comes on the show, and we'll summarize that in a nice article. And we want to thank you for your short appearance, and thank you for your time for being here.
Thanks a lot. It was great to be here.
Great. Hey, bye.
Have fun.
Needs a bit of a wiggle. Man, that's really small. Certainly not for manual picking and placing. Okay, that should be good enough. Resistors are fine. Coupling caps. These are do not mount, so we don't need them. Okay, this resistor needs to be moved down a bit, otherwise it will cause tombstoning. So both sides of the paste need to touch the pads. Let's slightly adjust the position of the memory. right? The accelerometer looks fine. Maybe move it tiny bit below. That was too much. I'll just move it back. All right, and then secure element. Maybe side view would help. Let me adjust the focus. Yeah, okay. It's aligned really nicely. And last but not least, let's check the temperature. Humidity sensor, which is misaligned. As the electronics industry moves forward, they are basically shrinking down all the parts, which makes it harder for makers and hobbyists to do the hand soldering. But on the good side, on the flip side, the manufacturing process becomes really cheap for PCBA. Okay. View it from the side. Pads are aligned. Okay, that's good enough. Okay, let me move back the microscope. Okay, now we have done the first part, which was placing the components and doing the inspection, aligning and everything on the back side of the PCB. And then now we'll place it inside the oven, and then let's monitor the reflow process, see how the results turned out. We can also do it on the hacked iron that I showed earlier, but unfortunately we are in a co-working space here, and I don't really want to trip the fire alarm, because once the soldering process in the open air, at least the reflow oven will contain that smoke a bit, and I will open the windows in the meantime. But if it's on the soldering iron or on a hot plate, and then that might emit more smoke. So let me change the view. And we will, if I can adjust the camera angle like this. Perfect. Okay, we have our thermocouple here, and it's connected to this basically reflow oven controller. I have a profile set up. It's around 200 degrees for this oven, and now I'm going to, sorry for the angle, carefully place the component, bring the thermocouple close. What I usually do is preheat the oven a little bit, so that we turn it on, both of them, and then we start. You can see the visual indicator here that when the oven is turning on and off. It's basically doing on-off control of with the PID. And we can also monitor the temperature here. Because the oven is really cold now, I will do the preheat twice, and that will make sure that we have enough heat built up inside. Now we stop it and we start again. We need some light inside. Also, I will open the windows just in case. For those who don't know, so reflow process is basically, you can see the stages here, and we can adjust the time, we can adjust the temperature of each stage. I'll briefly show you how each stage means. Basically here is when the soldering process happens. And depending on the solder type, depending on the PCB size, many other factors, we can adjust these parameters. Right now we are doing the preheat, which is this phase. Then it will slow down a bit, and the controller does this sequentially, like at a slow pace, not to cause any thermal shock. And once the soldering process is done at this phase, then also it's not a good idea to remove the PCB immediately, because then everything will cool down real fast, and that will cause thermal shock again by cooling it down instantly. So you have to leave it in the oven a little bit and then let it cool down. And I will also open the door of the oven slightly, so to speed up that process. Okay, let's switch back. Now it's soaking. That's around 130 degrees. In the meantime, I'm gonna clean up the desk for the next phase of our soldering session. Hopefully this one turns out a success, but we will verify that under the microscope. Okay, as you can see from the controller, reflow process started. Now you will see the temperature rise up real fast. I'm using leaded solder paste just to make it easier, also to solder things at a lower temperature, not to cause any component damage. But in real life applications, all these soldering processes, they are using lead-free.
Hey, Orkhan is soldering here. Hi, Mark, how are you? We have another
Fine.
IoT expert. So, same question to you. What's your IoT advice for IoT developers for 2022?
Yeah, first of all, I don't want to interrupt this live soldering session. This is so amazing. I'm completely astonished.
It's
Actually,
cool,
I
right?
would like to have the pulse for soldering.
Yeah.
But
Cool.
yes, a good job. So going to your question, yeah, I think 2022 it's a really exciting year for IoT. Actually, yeah, I'm, well, let me introduce myself. I'm Mark Bose. I'm developer advocate at Belina, and we are trying to help companies that have fleets of devices, like for example, if you have a fleet of LoRa gateways. So we help to reduce friction to update the software of this fleet of devices with Belina. And I think for 2022, yeah, the goal must be to everyone to try to reduce friction on everything that we do. If it's visualizing data, have APIs, or help people to connect devices, or whatever we do, or update software, we just, I think, try to keep to reduce friction. What do you think, Vinka? Does it make any sense
always.
to you?
No, for sure. There's a lot of there's still a lot of components that are really rough, like definitely that's something that always can be done better. And but so with Belina, you're working on remote management of Raspberry Pi like computers in IoT. So how do you guys do that then? That removing that friction?
So, our reduce of friction, the idea is to simplify the way companies manage the software updates on their devices that are remotely deployed. I remember one thing that it's interesting on Belina is that everyone does support. So that means that automatically, randomly, you get support scheduled on your calendar every week. And I remember giving support to a company where they had an issue on a device, and they need to take a donkey for 3 days to get to the device. And I'm sure some of the customers, at TTN, do the same. They have the gateways deployed on remote places where they need to take days to reach the gateway, right? So yeah, this is how, with Belina, we can help to access to the device easily and enable them to remotely manage the software without being need to go there and plug a computer and update the software, or go there with a mobile phone. That's it.
No, totally agree. I think all our users and customers that have proper remote management of these LoRaWAN gateways, they save themselves always a ton of trouble when they are actually about to scale. So making it more easier, making it easier to integrate. I think we can all agree with that. So. Let's go back to this flow. What you're saying, I totally agree with you. Like just the soothing voice of Orkhan and the process he's doing it's really great to see. So let's go back to Orkhan, and thank you very much for your contribution.
Thank you for inviting me, and looking forward to see how this
We'll
is
see
being
each other
soldered.
soon. And we'll see each other soon, right, in Barcelona. Let's see where.
Indeed, yeah. So if anyone comes to the Mobile World Congress, we are preparing IoT Stars, so see you there.
See you there. Great. Hey, talk to you soon.
Bye, Vinka. Thank you.
Bye.
antenna angle. And turn off the oven. So, as this thing cools down, it is safe to touch. We can observe the soldering quality. Let's switch to the microscope. Okay, starting from top. Everything looks to be soldered. The lid. Okay, all the sensors are there. It is also a good idea after soldering phase, if you are not sure, because some of the components we cannot see the pins, they're underneath. We would like to check the continuity between VCC and ground pins, just to see if there are any shorts before we actually power this up. But other than that, looks pretty good. Let me quickly check the continuity. Okay, that's gonna be between ground and VCC. Also, let me check the sensor VCC line. So we'll go to the KiCad view, we go to the bottom layer, increase the right, and then see which test point is actually for VCC to sensors, because we are switching the VCC line to sensors with a load switch to conserve power. So that is this one, and the silk screen on the back is a test point 11. So TP11 is the VCC. All right, let's test between ground and the TP11. See some 500K, which is a good sign. Means there are no shorts, that's the most important part. And then I guess we are done with the backside. We will come back at the end to solder the push button manually. But other than that, I think backside is done. We can flip the board and continue with the top side. Now I think it's gonna be an interview. All right, now let's move on. Okay, now we have soldered the parts on the back. which also means that it's not very flat anymore. We have to compensate for that when we place the stencil for the top side. So what we're gonna do, as you can see, if we hold it on the side, the tallest component are the caps, 0603 cap and the accelerometer. So it's around 1.1 millimeter. So we're gonna use another one of these PCB to lift this up, and then hopefully we'll be able to place the stencil. All right, remove the old one. We switch to the workplace. Okay. Let's get rid of the multimeter. All right, as you can see, it's not flat anymore. But for good solder paste application, we need it to be flat as possible. So what we're gonna do, we're gonna rearrange the PCBs. I'm gonna remove the magnets. So this metal platform is actually has the same height, 1.6 millimeter standard PCB thickness. So what we can do, we can place the top edge of the board here and place a couple more on the side, so that way we'll have a good alignment. Then we can use magnets, because that will help even through the PCB to keep the board in one place. It's not as strong, but it does the job. So let's make sure that there are no components underneath. And also from here. I'm gonna actually place one magnet here. Okay. Let's see if the stencil fits. It does, but we need support underneath here. So that can do. Can take another one of this here. Then, but we need more PCBs. Now we have a double stack. Let's push the magnet. I'm gonna use one of the strong ones. Actually, we do have those fridge magnets as well, so we can also use those. They also help to keep everything stable. You can stack them up. Let's make sure not to apply too much force from the sides. Otherwise, it will just flip up. We have to anchor it as much as we can so it stays in place. And the magnet is your best bet here. Okay, nice, just to make sure everything is good. It's very tight fit now. Okay. Let's use one more magnet. I'm going to use this one here. And then we can use some more tape just to secure everything. Get rid of the magnet. I'm gonna clean up the surface a bit, just get rid of all the contamination during the PCB production process. That helps to stick the solder paste much better. Now, yeah, it is pretty stable. That's good. Now we placed our stencil. Let's see if the alignment is good. We have to remove this one. Let's find the solution for this. Right, now we have this fridge magnets stack. Let me use the straight part. Right. One more. Perfect. Now it's much more stable. And now we can apply that stencil. As you can see, the tape is in the way. It actually adds a little bit of thickness to the board, which is not very good, so we're gonna move it a bit to the side, and then also from this side. this PCB adds too much thickness, I guess I'm gonna have to use something different. Okay, let me try the magnet. Let's check it now again. Still, as you can see, there's a bit of a height difference. So what I'm going to do is actually open this up. And then take some more PCB. And then one more. Hopefully that will I've also shortened the stencil a bit. Now we should have a better attachment to the surface. I forgot to put this one back. Let's put another magnet. So one of them strong ones. That will do the job. Okay, one way to check the alignment is to shine light from different angle to your PCB. Then you can see if the components are misaligned, and you will see some dark spots. Let's double check. Actually, on this PCB, the most difficult part to solder and also to get the solder paste right is this one. As you can see, that is a BGA part, which is a buck boost converter, RP605. That one is usually the hardest one to solder and also to make it right. Usually takes a couple of reflows. And so we can see on the top side, needs a bit of a shift. On the bottom side, looks fine. With the good solder paste application also will give us much less headache at the end when we try to run the device. We wouldn't have to do the debugging for the shorts and for cleanups. Okay, this looks good. Now we're gonna carefully tape the stencil from each side, just to hold it in one place. Okay, I'm gonna do it from this side. One from top. careful not to apply too much force and shift the stencil underneath. So okay, that looks good. I think let's have a closer look. All right, I guess looks good. Just do a final check. As you can see, it moved underneath, so the PCB is not very. Seems like PCB underneath is not that stable, which might be problematic. Yeah, let's open it up, make sure everything is aligned, it's fixed, so that we can have successful solder paste application at one go. You can see, okay, there's a little bit of gap. That's what causes it to move underneath. It's really hard to fix it. Now we need to take a different approach. Maybe with the magnets might help. Okay, yeah. I see what's the problem. So previously, if you remember, we have 2-point support, so the side walls from this platform. But right now we removed it because we have to lift up the PCB. Now we have only support on one side, but all the other 3 parts, even though we have installed magnets, it doesn't really help. So we're gonna have to make sure that we use tape, but we're gonna use different tape, which has much smaller thickness. Normal Scotch tape. So, okay, the first PCB is attached. Now we're going to do the second one. Okay, that is better. And we're gonna do one more to this PCB. Let's make sure that the PCB doesn't slide underneath. by just wiggling it. Okay, there's a little bit of a gap. Looks like this PCB side is not very clean. This is cleaner. Clean this up a bit. Let's use some more magnets. A piece of tape so it can stick better to the metal surface. All right. Now that's much better. Now we put back our stencil. Make sure the alignment is good from every angle. Okay, magnets are really helpful here. Okay, I'm gonna adjust a little bit. Just the small tweaks. Looks good now. Looks much better. Okay, I'm gonna apply some light. All right, that looks good. Means we can fasten the top side stencil now and then go ahead with the solder paste application. I really hope it's really hard to see, but looks like the BGA part is also aligned. Actually, let's do the microscope checking. Switch to the laptop. As you can see, the alignment is good enough. Most important is the, sorry for the shaky image, most important is the BGA part. Okay, I'm gonna looks good. Now we can use some more tape, if we can find where it is. Maybe one more magnet on this side. Okay, now we can apply the solder. Okay, let's take out our syringe and this time we're going to use a bit more solder because we have a lot more openings and they will require more. And hopefully we will be able to do it at one go. So maybe I can change the angle to get a closer view. As you can see, I'm applying at a 45 degrees angle and uniform pressure. Hopefully we'll do it at one go. Okay, 3, 2, 1, let's go. While holding it down, we do another run for cleanup. And hopefully that should do the job. Now we have to carefully move the magnets. That's going to be tricky because we've applied so much tape. What we can do is to very carefully cut that tape without causing misalignment. Okay, now we carefully lift the stencil up. Remove the tape. Hopefully lift up everything. Perfect. Looks really good. We will gonna check it underneath the microscope again, but looks better than I expected. Very carefully. You can see. Let's carefully move it aside. As always, I'm gonna clean up the desk again so we can have a also clean up the stencil. Never leave the stencil with the solder paste on, because if it dries up later on it's going to be really hard to clean it. Sometimes it's also a good idea to wash the stencil under the hot water, because alcohol or isopropyl IPA won't go in, so it's better. So what I do is usually like this. I put one cloth underneath, then apply some alcohol. Then take a brush and basically just clean it up like this. So hopefully you want to get a brush with very fine tips, and then hopefully clean it up. But it's also a good idea to wash it underneath the sink without soap, just water, normal running water. And that will clean up the solder paste, and we can basically remove the tape. Yeah, that's good enough. And then, okay, we'll get rid of the platform for now. It did the job, we don't need it anymore. Get rid of all the, okay, this on the side. Okay, our main PCB is here. Let me bring the microscope to check the solder paste application. Hopefully we have a good one. It's not focused, so yeah, we have a bit of a misalignment, but that's no problem. It's not off pad. That's as best as we can get with the manual inspection. The important one is the balls on the BGA part, which is this one. So as long as the part of the paste is on the ball, is on the pad, we should be fine. The MCU looks fine, and yeah, big parts are okay. Cool, and this is the last one of the antenna. Very nice. That means we can move ahead with soldering, or actually first placing the components. Let me bring back my component board, and then we will start placing components same way we did to the back side. Now I would like to take a short break, and we'll be back in 5-10 minutes. So, hey guys again, we are back after a short break. For those who are joining now, I'd like to welcome them. Welcome to this session again. My name is Orkhan, and we are doing a live soldering session of the generic node. On the first part, we did the backside of the PCB, and which was successful, hopefully. And now and at the end of the first phase, we applied the solder paste to the top side, and now we're gonna place the components to the top side and then do the reflow of the top side. Before we do that, I would like to, there was a couple of questions in the Q&A, and then I would like to answer those questions. Let me switch the view. Most of the questions are actually about the gear that I have. Most of them are mine, and I'm using it in my home lab during the COVID time, where we were working remotely from home. Let's start with the reflow oven, standard 852D+, standard Chinese reflow oven you can get. It's usually around $50. And then I have a really functional and useful, also not too expensive microscope. It is a USB microscope. I have it connected to my laptop. And once you plug in, it appears, so you can choose whether to be a PC camera, like a normal webcam, or as a mass storage device. And it has a SD card here. You can take a photo and video at 720p. So it was around $45–50 also. I also have here OT Arc, my trusty power supply. It's more than the power supply, and we will run the generic node with this and set the current limit and look at the waveforms and the current consumption. And here I have a small helping hands. It's from Lidl. It's also was quite cheap, around $10, I believe. And this one I have TS100, and with a couple of, I can show you a couple of tips, so various tip sizes. And the big thing here is the reflow oven. So this comes from the company called Beta Layout. I believe they are based in Ireland. So they are selling this as a kit. The oven is also included, which is a standard oven, non-hacked, nothing. But it has this nice controller. The metal platform also comes with it that I use a lot. The magnets, squeegee, this one, metal squeegee, and the solder paste applicator, like this. I don't know what is this tool called, but basically for the solder paste like this, you just grab it like a spoon and then apply it to your stencil. As a solder paste, I'm using the ones from Chip Quick, which works really nice for me. They are leaded solder, which makes the soldering process easier for the live sessions, but normally in the manufacturing process they don't use leaded solder anymore. Other than that, yeah, I have an anti-static mat, and I have a small bracelet here, which is also grounded. I'm gonna wear it. Actually, I have to wear it now, but it gets in the way, sometimes touches the solder paste and basically destroys the PCB. Right now we are not doing anything. We are not powering it up, but once we power this up, I'm gonna wear it. Hopefully I won't forget it. And I also have a multimeter. This is a EEV block branded BM235. It's a really good one, really solid, and it's my go-to multimeter for over 5 years now. Okay, any other questions? As a software, okay, what software I'm using? So right now we are using OBS Studio to do the streaming. but I've used KiCad, started with the KiCad version 5 to design the generic node. Then later last year, around Christmas time, they released the version 6, and I ported everything to version 6. And right now in our repo, the files can only be opened with KiCad version 6. And the BOM file, the interactive BOM that you are seeing, this is also generated inside the KiCad. I would like to show you quickly. So basically it's the interactive BOM tool, and you can add it from the, I believe there's external plugins, yeah. KiCad version 6 made it really nice, so you can add external plugins very easily. Okay, I think that's that. So basically, we are pretty much done with the bottom side. Now we flip the board view to the top side. As you can see, there are much more components here, and it's going to take a while to place them all. But yeah, those are logos, which we don't care. And as always, we'll start with the capacitors, then we'll go to the resistors, and then inductors. You know the drill. Okay, and let's start. Okay, this arrangement looks better based on the reference, which will also coincide with the BOM list we have here. Okay, let's get started. Now we pick our tweezers. Oh, by the way, for picking and placing, use different kinds of tweezers for different component types and placement types. This is the one I use mostly for picking and placing. This is the one I use when I do reflow soldering. I also have a flux here, also from ChipQuick. It's also a really good one. It does say that it's no clear, but you still have to clean it up. Okay, let's start from the top with the antenna. Okay, this antenna is from Ignion. So it's called NN02-201. It's actually very small, and it has a quite wide tunable range. It can go up to, I believe, 5.8 gigahertz Wi-Fi. So it's basically a small IoT antenna, and the orientation doesn't matter. We can place it any way we want, but just to keep some of the OCDs lined, I'm gonna do it the way all the other generic nodes have been placed, like this. By the way, these are not hand soldered. These are assembled at the PCB factory in China by Esd Studio. Okay, we place the antenna. Looks good. We go to the next one. We source them all. Now we place the antenna. We go to the 100 microfarad caps. So these are basically the bulk capacitors. In any battery powered or solar powered IoT device, you really need to have a bulk capacitance at the input power stage. Then that would make sure that the device doesn't brown out. So we'll place these ones first. And then the next one. And we have one more here. Very nice. Okay, that's done. We go to the next. Next one is 1 microfarad caps. As you can see, there are 4 of them. And from our list, we go to the 1 microfarad. Where is it? Where is it? Here. Yep, we have 4 of them. Pick first one. This is for the first load switch. These are the 2 load switches we are using to switch off the power, basically completely cut the power to the sensors and to the flash memory. And this way make sure that we can achieve lowest possible power. But they need input and output decoupling as well. As you can see, I'm using SOT23 parts, which are the most widely used for this type of components. So I touched the antenna. In this day of age with the component crisis, this was actually really a good idea to use standard footprint parts, because then if one component is out of stock everywhere, you can most likely find a drop-in replacement from other vendors, because if it's a common footprint, then there's a really high chance that you will find the replacement part for the which also pin-to-pin compatible load switches, for example. Now we do the first 1 micro is placed, then place the second one to this load switch. Then the third one, that is for the input. Goes here. As we did with the bottom layer, we will inspect everything under the microscope and do the realignment if necessary. Okay, 1 more, which is here. After some point, your tweezers might get sticky like this. So because of the solder paste is getting to the tips, and then once you place the components, components stick to the tweezer. To overcome that, basically need to clean it up periodically. Let me adjust the angle a bit. Okay. Now we can continue. Okay, so 1 micros are placed. Next one, 100 nanofarad, and we have lots of them. They are the most used capacitor type as a decoupling capacitor, and then basically we have to. There are around 8 of them, or no, we place 5 on the back, and then we have 12 on the front side. Okay, let's go ahead. So these are the 100 nanofarad caps. We will start from the top, which is the reset button, or next to the reset button. That is to smooth out any power surges or ESD shocks on the reset line. And then We have one more for this RF switch. So that means that goes here. And close. Very good. Next one is the decoupling for the microcontroller, which is the STM32WL, and we are using a QFN package, QFN48, because that is easy to solder manually. And it's also cheaper to fabricate at those PCBs, because then you don't need via in pads or very small via diameters. That makes it, you can use standard 0.3 millimeter drills. We have one more here. And one more here. Moving on, another decoupling cap. As you can see, they are as close as possible to the MCU. It's actually, the correct definition for this is actually SoC, system on a chip, because it combines an MCU with a LoRa transceiver. All right, next, another one goes here. Two more. Most of these 100 nanofarad caps are decoupling caps. As you can see, this is the section of the power supply of the SoC, and these are all decoupling for the main VCC line, also for the ADC. Very good. Next is, okay, we have 5 more left. Next one is this. Then we rotate our board. One more goes to here. And the other one goes to here. Sometimes the components are really dense and really close to each other, and makes it really hard with the tweezer to place one of them or the other. Then we'll place it a little bit to the side and then just wiggle it until it finds its position. Okay, looks like we are done with the 100 nanofarad caps. All of them are placed. I'm just gonna double check with the BOM file. Right, very good. Let's continue. Now we are doing the 22 microfarad, which is this one. It's in a bigger package, it's a 0603. It's actually easier to work with. This goes here. We have a couple more big ones, those 4.7 microfarad caps, or MLCCs, multi-layer ceramic capacitors, as they say. They will go one to here. These are also bulk decoupling for the SoC. One goes here. And the last one of the 4.7 microfarad goes to here. Very nice. Now, that is also done. Just bear with me. There are many small components, especially the inductors and capacitors are huge abundance here. Okay, now we're gonna do 33 picofarad caps. Most of them are RF parts, which will be positioned around the antenna path, RF path, and some of them are here. So let's not waste time and go ahead with the 33 picofarads, which are here. Okay, let me zoom out a bit. So the first one goes to here. The second one goes to the low power path. The third one, okay, it's right at this point. And the other one, let me double check. Okay, here. Really nice. Now, next one. And the last one of the 33 pico caps goes to here. Let's double check. Okay, we have successfully placed 7 of those. Done. And we can go to the next. C23, 47 pico. And that is here. Looks good. Next, C25, and that is 47 nanofarad. Which goes to here. Very nice. C26, it's 68 pico. 68 pico, 26. Goes here. Very good. I guess the angle would be better if it's closer. The next C28, 417 nano. That one is actually a bigger part, 0603. Yeah, that is used for, so this SoC has a nice feature. It has a built-in switching regulator. It has actually 2 regulators. One is a linear regulator, which is used by default, but if you want to save even more power, you can enable it inside your code and then use the switch mode power supply, and this cap and the adjacent inductor is for the built-in switch mode power supply. So that was C26. Now we go to some more RF parts, which is C30, 37 and 44, 2.7 pico, 3 of them. And they are placed vertically here. That is the first one. That is the second one. Make sure that alignment is good, even though I can't see much. And the last one goes to the RX line. Here. Very good. Now C31, which is here, 3.6 pico. That one goes to here. Okay, it's because of the close proximity, it's really hard to place two small components side by side. This is as best as we can get. Let me actually try the microscope. I don't know if it helps with the view. We have this small table microscope. Hopefully it increases the visibility for you viewers. It certainly does for me. But gets in the way. No, it's actually blurry. Yeah, not gonna use it. So with this C31, as I go, I'm just clicking that as it placed. C31, done. C34, 10 nano, okay. Is this one here. And goes to here. This is probably for the TCXO, temperature compensated crystal oscillator. Yeah, we are using a TCXO instead of regular oscillator because that gives us better stability and good clock source. And C34 done, C35, 46, and C49, which is 5.6 pico. Okay, 3 of them. 1, 2, 3, and they go horizontally, so don't need to flip the board. First one goes to here. Second one, and there's also a secondary oscillator, which is the crystal oscillator. This is a low frequency 32 kilohertz, and that is used for real-time clock of the SoC. Then we can use a real-time clock, and we can completely go into the deepest sleep mode, and then periodically wake up with an interrupt from the RTC, and then send the Lorawan packages. C36, 6.8 pico. That one goes to here. C39, which is 3.3 picofarad. C39, Okay. All the way up here. C38, 2.4. That one goes to here. Very good. Almost done with the caps. C40, 3.9 pico. Very good. And then the 1 nanofarad caps. Those are these ones, C43, 47, 48, and 50. C45, okay. Let's first place the C45. Just one single one here. And this one goes to input of the RF switch. This is the RF switch. I'll try to speed up the process a bit, because if we wait long enough, then the solder paste will dry up and won't stick to components anymore. But we can speed up so much because of the large quantity of components. Okay, now we do the 1 nano, which we have 4 of those. 1, 2, 3, and 4. Two of them goes to here. One of them goes to decoupling to the RF switch, because the power to this RF switch comes from the GPIO pin of the MCU. One more goes to here, which is really at the tricky spot. Hopefully we can place it. Okay, that will do the job. All right, looks like the capacitors are done. Now we have the diodes. Starting with the input diode. This input diode is actually a Esd protection diode. So this is from some Esd that might be coming from your battery clips and connectors. And this one is D1. Good. Next, D2, which is the flyback diode of the buzzer. yeah, we also have a buzzer here. Let me switch the view. That is the buzzer waiting for us to be placed. But first, let's place the diode. We make sure that the orientation of the diode is correct. So the mark on it should match the mark on the PCB silk screen. So I'm just gonna make sure under the microscope that it is correct. Yeah, it looks to be. Goes here. Looks good. Next, D5, which is the really small Esd diode for the reset button. It's this one. I hope you can see it's very small, I guess. I believe it's even smaller than the 0201, or maybe it's the same size. The package for this is actually SOD323F. So we're gonna make sure the microscope that the orientation of it. So I have to rotate it. Then hopefully it's aligned. Okay, one more. This is probably the hardest component to place. To be very steady and very careful. Very good. Next, we can actually place the reset button, which is here. In the future versions, so this is a very low profile reset button. Usually reset buttons are not very frequently used, but in case you want to use the reset, you can use like a screwdriver or a pencil tip and just press this one here. Okay. Then we do our resettable fuse, poly fuse. This one is rated around 1.5 amps. In case there is a short. Actually, our buck boost converter also has a built-in overcurrent protection, but just in case, if the short happens before that, then we have another safety layer. And then we are going to place a ferrite bead, which is a filter element for, so placed F1, which was the polyfuse, now FB1. This is for the ADC reference voltage. And also I believe ADC power supply. Basically here is the filter section for that. Here in the interactive BOM file we have a bunch of logos. We're gonna skip those. Sorry for the background noise. Looks like there's a construction work going. And now we're gonna place the clips. These are actually small clips. I'll show you on the. So took the clips to hold the RF shield in place. So our RF shield is removable. If you want to look inside, pick inside the board, or change some components, you can easily do that. But for that, in order to do that, first we need to solder these clips. So first clip goes to this spot, and we have to very carefully align it, otherwise it makes it really hard to plug in the RF shield. Right, the next one. Okay, now is the time to clean up our tweezers again, because it seems like it is sticky. Right, now we rotate our board and then place the rest of the clips. This one goes here, and the last one goes to the top. From the outline, you might observe that our original idea was to keep so this is part of the antenna tuning network. So those components, the pads for the components, and we wanted to leave that open, but it made it a bit hard to produce the custom RF shield. So we just went with the rectangular instead and have an opening here. Even though it's a custom RF shield, we also the outline is pretty similar to one of the off-the-shelf ones, but that needs to be manually modified. Basically, this cutout has to be manually created. Hopefully, surface tension of the solder will align those clips better. Let me just align them as much as I can, but then leave the rest for the reflow process. All right, the clips are also done. Now we do the other small parts, like, for example, the inductor, for our buck-boost converter. So it goes here. It was a real challenge to gather all those components because of the ongoing component crisis. And we basically had to get them from different sources, and we managed to fabricate around 500 of these boards. And it was a big hurdle, but at the end we managed it. Now the only things left is to finish with the certification, and then we can start shipping them. Okay, now we have to do the UFL connector. Let's double check the pin. Okay, we have to rotate it, and then you can use it like this. And carefully place it. Perfect. Next, okay, we have now the inductors. switch to the BOM view. So we have those in the list, but we're gonna skip them to the last stage. We did this one. We will do them manually, also manually later. Also the through hole part. Then we start from this. We did this one, and then now we're gonna do L2 and L9. So L2 and L9 are 3.3 nanohenries. I really love this blue inductors. Let's have a look at one of them under the microscope. As you can see, there's a really small let me try to get a better view. I hope you can see the windings. That's really cute. Yeah, you can see the copper winding. It's really nice coil. Even though they're small and hard to solder manually, but it looks really nice under the microscope. Okay, these were L2 and L9. Which will go vertically. That means we have to rotate the board. This first one goes to here after the cap. And the second one goes to here. Very good. Now L3, which is 3.6 nanohenries. That's one. Goes to the corner of the high power path. This radio module, or the transceiver just inside, it's SX1261, I believe, and it has a high power and low power outputs. So the high power is more suitable for US market, and it can do up to 22 dBm. And this is this path. The low power one is this path, and it can do maximum of 14 dBm. Here in Europe, we are using low power path only, and that also consumes much less energy. Even if you use a high power path set the output power to 14 dBm, it's going to end up consuming more power than this at the same power level with the low power path. So L3 we did, now we're going to do L4, which we mentioned earlier is the built-in switch mode regulator of the SoC, which goes to this spot. Now we're going to do L5, 11 nanohenries, and it goes to the opposite corner. It's really hard to see placement, but hopefully the alignment is good enough. And these three components are on the receive path of the antenna, from the antenna to the microcontroller, and they are converting the differential signal lines, RF lines, to the single-ended. Very good. Now L6 and L7, 47 nanohenries. They will go to two of them, and they go to one for each RF path. So this one is going to the high power path, and the other one to the low power. Let me double check the placement. That is good. Okay, need to rotate it. Sometimes flips, so the blue side has to be facing up. Now it's really hard to spot. Let me try the other tweezer. It's good to have the different tweezer types. It makes it easier. Okay, okay, it looks good. L8 is this one, 3 nanohenries, and that one goes to here. It's also a tight spot, but looks like we managed to place it. Next is actually another inductor. It's more like a ferrite bead. It's L10. It's this one. Which is also being used for the TCXO. It's actually a power filtering for the TCXO. It's also in a tight spot with small components around it. Makes it a bit hard to place, but I think it looks good. Let me wiggle those components a bit. There we go. So we have 5 more inductors left. So L10 done. L11 goes to the top corner, which is 6.8 nanohenries. And that one goes to here. But it looks like with a bit of an error here. So this one is L11. That one is 33 pico. Means we did place this component wrong. We have to shift it a little bit to below, and then place the inductor in its place. and hope that some slightly misaligned components will self-align itself during this reflow process. Very good. Next, L12, which is sits on the other side. L12, 8.7 nanohenries. That one goes to here. Very good. Yeah, that won't move anywhere. Now we do the L13, which is 27 nanohenry. So L13, 14, and 15, let me show you on the laptop view. So these three are forming the what's known as matching network tuning. So these are tuning the antenna's resonant frequency. In this case, in our case, it was 868. And even though it's tuned more for 868, it will still perform decently with 915. But by just playing around with these values, we can change the antenna to up to 5.8 gigahertz. So has a very wide tunable range. It's a very small antenna. It's easy to use, and Igneon, or with the old name Fractus antennas, they were really helpful with tuning this. But usually with a small antenna like this, yeah, don't expect nice range or good RSSI. So range might be affected by it because it's very small and it's physics. You cannot do much about it. If you want a good range, you have to use bigger antenna. Okay, now we do the L13, I believe, yeah, which was 27 nanohenries. This one. Okay, that's the first one. Then L12, no, L14, which goes to the ground. Very nice. And the last one of the inductors, which is L15, that one it's right in line with the antenna, so we have to rotate it, and one more try, and then goes here. Very good. And that concludes the inductor part. We are almost there. And now we have to do the resistors and the rest of the ICs on top. And then we'll do the final check under the microscope, adjust the components if necessary. Okay, now we do the... Okay, and zoom out. Okay, we're gonna skip the piezo for now because it consumes lots of space and we have to place other components around it. So what I usually do, place the small components first, And then at the last step, place the bigger components, also the MCU. So now we're gonna do the transistors. So Q1 is actually a MOSFET, P-channel MOSFET. It's a reverse polarity protection MOSFET. So it's really helpful if you plug the batteries in the wrong orientation, and protects the board from being fried, basically. Just one component added. Not much of a bomb cost, but it's really helpful, because in case you plug in the battery here, even though it's clearly marked, both batteries goes this way. Sometimes, yeah, it could be that somebody plays it wrong, and then you get negative 3 volts at the input, and then that could easily ruin your day, fry everything on its path. Actually, this Esd diode is the first line of protection, and this reverse polarity protection MOSFET is the second and the main one. Okay, Q1 is done. Now we do the Q2. These are the part numbers. I hope you can read them. Q2 is actually located here. As you can see by the close proximity to the buzzer speaker module, it's running acting as a switch for the buzzer. Okay, next, resistors. Almost there. Yeah, these are the last part. R1 and R9. Yeah, that's the interesting one, because here you can see we have a resistor switch changing the path from the antenna to the UFL connector, so you can connect a external antenna. In order to do that, you remove the shield. You basically take a soldering iron or hot air station and desolder this part, change the path, and solder it back to this points, basically between these pads. Right now we're gonna point it to this direction. So R9, 0 ohms. So our R9 is here, just one of them, and that goes like so. Looks good. Next is 100K resistors, which are pull-down resistors for the load switches, I believe. As you can see, two of them goes to load switch, and then one of them goes to the voltage supervisor. Yeah, we also have a voltage supervisor chip. That really helps with if the battery is low or battery is dying. It will cut the power so that the board won't become unstable anymore. So 100K, R2, R3, R9. Oh, R4, sorry. Yep, and those are here, 3 of them we need. First, this one, and then this one, and the second load switch. So these are pull-down resistors, as I mentioned earlier, and the control pin, it keeps the control pin low if the MCU is in a floating state. The GPIOs that are coming from the microcontroller are in a high impedance state, then this will make sure that low switches are off. So next, 220 ohms, which is R5. And that one goes to the output of the TCXO. Very good. Next we have R6, R7 and R8. I hope you can see them. Let me move the component board a bit. So R6, R7, R8 and R24. These are 100 ohm. And then we need 3 of them. 1, 2 and 3. So one goes horizontally and the other 2 goes vertically. Very good. Now we have 2 I2C lines on the board. We did the first I2C pull-up resistors on the back side, which were 4.7K. Now we do the second 2, and they go to here. Sticky bit. Very good. Not much left actually. Most of the painful components are placed. R16, it's a 1K. Goes here. We have another 33 ohms, which is for the buzzer. All right. Now we have another 10K, which is here, and then that is for the boot 0 pin. So that pin has to be pulled up, otherwise microcontroller will not boot from flash. If it's not pulled up, it will boot from, it will wait for a bootloader. So the bootloader will jump in and it will wait for a new flash image from the serial port. Actually, you can use this one, and that's why we have a jumper. You just connect the jumper or short the jumper, and it will wait for the serial upload. But normally we use a ST-Link like this one or any other ARM programmer to do the SWD programming. So it's called serial wire debug. All right, and so I think we are done with the resistors. Let me double check. Done. We also did the reset button earlier, and now, yeah, these are, so it's a TPS 22917. It's the load switch that we're gonna do. Let me make sure the pin 1 orientation is good. Actually, there's a cool trick here. You can highlight the pin 1. This shows where the pin 1 is located. And in the chip itself, it's also marked. Oh, it's focused. Focus. So this way up, this one on the left right corner is the pin 1. That's what we need. So we carefully place it and then rotate and place the other one. Very good. Now we are done with the surrounding of the oh, actually there's one more component missing, which is this one, a voltage supervisor. And we place that. And now we can place bigger components like the buzzer. You can see it's clearly marked, the output port of the buzzer, sound port, where it's located. So we did that. Hope the alignment is good. What's left? RTC clock. So this is the RTC clock. So we place this and this. So these are all we have left. RTC clock we placed. Now let's do the TCXO. As you can see, the pin 1 mark. So it's a bit hard to find where the pin 1 is located on the TCXO. But let me show you quickly. Under the microscope, we can figure out where it is. So this is the TCXO. It's a very small part. Usually pin 1 is indicated with a diagonal cut, and that's the one here. And if we flip the that's a 32 megahertz. And there's also a small mark here to indicate the pin 1. And you're gonna place it as it should. Very good. Almost there. Now what we have left is the microcontroller and the regulator and a couple of these connectors. Let's head back to the BOM. Okay, now we have RP605. This is a 2.8 volt version, but there are 2 volts, I believe 1.8 volt output, 2.5, 2.8, 3 and 3.3 volt versions. So you can see the pin 1 mark, and that part is also really small. Let me also show you under the microscope how it looks. This is the only BGA part. You can see the solder balls underneath. Let me focus it. Yeah, there we go. You can see the silicon actually shining. Oh, that is really nice. So this is really highly integrated chip with many functions, and you can see the pin 1 mark, circle facing. It's on this side, so pin 1 is here. And it aligns with our PCB. So we're gonna place it carefully. This is one of the critical components and easy to mess up because it's a BGA package and it's hard to do. That's why I'm gonna do a close-up view so you can also see what's going on. Gonna very carefully place it. And hope that it will self-align. As you can see, you can visually inspect and be sure that it's aligned well, because it sits inside the rectangle. All right, the next is a small analog switch. It's this one. It's also not so easy to solder or see the pads, but you can see there is a small pin 1 mark which is aligned with our board. Let me clean up the stencil, this tweezer a bit again. All right, now I'm going to carefully place it. It goes here. Let me show you actually on the laptop. So we placed the buck-boost converter and we have 4 main ICs left. So that's STM32WL, our main SoC. This small analog switch changes the power routing of the RF switch. Then we have the RF switch itself, and we already did the TCXO crystal. So now let's do this one. So as you can see, the pin 1 mark. Okay. Let's place it very carefully. Super steady. It's really hard to do it with the camera getting on your way, but let's give it a try. So looks okay, but let me move it a little bit to the left. We're gonna have to verify this under the microscope. Okay, that looks good. The next critical IC and hard to solder one is this small one. The pins are underneath. It's really hard to see. Okay, let's look underneath the camera, underneath the microscope. Let's change the view. Okay, this is our part. If we flip it, you can see, yeah, it's very similar to the BGA part, in the case that we don't see the pads underneath, so it's going to be hard to verify whether it's soldered properly or not, but let's give it a try. So that is this one. It's a BGS 13S4N9. And the pin 1 mark is actually in the lower right corner. So let me align that first. It's really hard to see where's the pin 1 because this is like 1 by 1 millimeter by 1 millimeter part. But yeah, I can see with the small microscope. Let's now also place this very carefully. Make sure that it is inside. So all these footprints are custom designed. When I design them, I make the silkscreen lines slightly wider, so it can also helps while manual soldering to see the alignment. Okay, this looks good. Our last critical component, which is also the main one, is the microcontroller SoC STM32WL. Oh, this is cool. This tool is really good. You can also individually select the lines. All right, so our MCU, you can see the pin 1 mark, and also in the lower right hand side. Let's change the view. Carefully place this one as well. Alright, alignment looks good from that side. Almost there. Now we place the quick connector. And the JST connector for our battery. Very good. Guess we are done. That means that all the components are placed. Let me just verify everything first visually, then we'll go under the microscope. Okay, let's do it under the microscope. I'm gonna bring it down. Very good. So let's start from the top side, and as we move down, we will align the components if we see them that they are misaligned. So starting with the, I'm going to use different tweezers for this. So matching network inductors, they look good. Maybe slightly this one. Okay. Our 0 ohm resistor, the jumper resistor looks good. The RF can clip needs to be shifted a bit to the left side. So UFL connector looks good, but the RF switch doesn't look good because it's really small. So we're gonna nudge it a little bit to the side. That was too much. Okay, that's better. And just carefully press from top to establish better solder paste connection to the pads. Okay, it's very hard. Okay, that looks better. Now, the rest of the components on the RF path. So these are the low power path. We can slightly adjust them. Good enough. Okay, these are good. Okay, this analog switch looks good. You can also double check it from the sides. Pin alignment. The lower portion of the RF, also good. As I said, like small misalignments like this, it's actually okay because it will self-align. We will double check that after the solder, after the reflow. But this one, for example, is not very good. So this inductor needs to be pushed back a little bit. Okay, that should do. And this cap might tombstone, so we have to shift it a little bit to the right side. Okay. Moving on. The reset button needs to be pushed down. These are okay. This one, small nudge would do the job. Okay, this clip needs to be adjusted as well. Okay, making it worse. Okay, that's better. Decoupling cap looks good. Let's move on. These are also fine. Maybe this one needs a bit nudge. This clip also looks fine. TCXO. This cap needs to be moved a bit. Okay. Moving on. This cap also. Okay, I need 2 hands here. Okay, it's very hard. Wait. This will definitely tombstone if we don't fix it like this. Very good. Also this cap. Let's check the MCU. It is one of the early production unit of this microcontroller. So as you can see, starts with ES, and that means engineering sample. So we got this at the early phases of the generic node.
production from ST. They were really kind enough to send us the early engineering samples, but it was fully functional, and that's what I'm using here. So the pin alignment of the STM32 looks good. Let's see from different angle. And the rest of the components, okay, looks good. Quick connector looks good. Okay, this one is the needs careful adjustment. So let's do that. As you can see, it's not perfectly middle. Small nudge, hopefully that will fix it. That was too much. Perfect. Then we just apply a little bit pressure from top, and that hopefully will stick it to the solder paste. And this clip also needs a bit of there we go. The rest looks good. Okay, I think we are almost ready to put it inside the oven. Okay, let's go back to the desk. So now, because we have a double-sided PCB, and that means if we put this one inside the oven as it is, because the solder will melt and the components on the back would just fall off, some of them at least. To prevent that, what we're going to do, usually in the production they are glued, so there's a tiny bit of glue which sticks them to the back, so that once they go through a reflow oven, they won't fall off. In our case, we don't have such glue or glue applicator, and instead we have this. It's a Kapton tape, so it's also known as a polyamide tape. It can withstand up to, I believe, 400 or 450 degrees, which is enough for our case. So we're going to cut a couple of pieces and stick underneath. So hopefully that will keep the components in place while we do the soldering. So let me cut a small piece. Okay, let's this view. Yeah. So basically, this is the back side, and we're going to tape it while holding it. So our tape, and without tilting the board too much, we're going to apply the tape. And also the second tape. So I'm gonna verify that tape is actually sticks well to the board and keeps the components in place. Can also do, just to make sure, have a cushion, like maybe a napkin or something, and then just apply pressure. Okay, that will make sure that the components will stay in place when we put it inside the oven. Okay, looks like our antenna, touch the antenna a bit. All right, the rest looks good. Now we can place this inside the oven. But we're gonna start with preheating the oven a bit. And very carefully place it. This is our thermocouple, so I'm gonna make sure that it stays close to the surface and not measure the air temperature, so that's why I have to glue it. Actually, let's do it this way. So it touches the surface of this dummy PCB and measures the surface temperature, not the air temperature inside. So we can place it in. Close it and start. All right, that is very exciting. I'm gonna pause the stream now and take a short break until this one finishes, and then we'll be back again. All right, we are back and our reflow process is finished. I didn't want to bore you with the same procedure which we already did once. And now let's turn this off and slightly open the door of the oven so the temperature would go down slowly. I'm at around 120, 130. We're gonna remove the board. Might be a good idea to put something to the door. Yeah, that could do. Okay, now it's around 168. $150. Okay. Almost there. Okay, the board is ready. Let's very carefully remove it. It's still hot, so while it cools down, I'm gonna tidy things up a bit and turn off the reflow oven. So now let's inspect it. Or better yet, let's inspect it under the microscope. As we did earlier, let's start from top. Antenna looks good. RF matching network looks good. The clips. Okay, the RF switch doesn't look good. We might have to rework that. Reset button. Okay, this looks good. The RF path components, no tombstoning so far. This analog switch also looks good. Our microcontroller. It looks bad, even though it looks bad, it's actually good. We just have to clean the flux because sometimes the flux would cause contamination and also introduce a bit of a low impedance path between the pads, so that's not very good. Definitely need to clean that up. Other parts looks fine. Most of the components are actually self-aligned. including the clips, the buzzer also. Buzzer is a bit off, but that's no problem. So this one, the buck boost converter, looks good actually. Probably we don't need to do any rework on this. Other than that, yeah, it's not bad for the first run. Let's turn around and remove the tape. And the backside components are still in place. Nothing shifted or moved around too much. Yeah, it looks pretty good. And the temperature humidity sensor also looks pretty good. That's very good. I think that's a successful result. My only concern is about the RF switch, that we might have to do a reflow, but we will see. We will see when we flash the board and try to send some RF packets. If we see the RSSI is too low, then we have a suspect. So let me also verify with the small microscope that I have. So now let's have a to-do list. First, let's solder the rest of the components. We have actually two types of pin headers. This one is the default one that we're using in our production, but in our last Q&A session with some of the users of the generic node, one user suggested this one, and I'm gonna give it a try with this one, see how it works. Hopefully that will. Okay, and I'm using a dummy PCB help with the alignment. So what I'm gonna do is basically to stack them together like this, and then it keeps the PCB in place. So we can take our soldering iron, and then start soldering the through-hole components. So let me bring the solder closer. Adjust the temperature. Here 140 would be enough. So now we're gonna solder the pin headers, and also as we promised, solder the button. Usually for soldering, I highly recommend using thinner solder wire with a rosin core inside, or flux inside, so that makes your solder job much better. Actually, first let's do the cleanup and then the reflow of the RF chip first. Then we will solder the SMD button, because the push button will get in our way and this will wiggle on the table a lot. So we keep that one for last. And now let's do the reflow. In order to do that, we need a stand, a good one. So I'm going to use this one. This will hold it in place nice and steady. I hope it's still in focus, but okay. And then we apply a little bit of flux. Surrounding the RF chip. Okay, let's turn on. Set the temperature of the hot air to 400 degrees. What we can do, actually, we can approach from the back side if there are no components. So in our case, as you can see, there are no components here, but that will take a while and we have to increase the temperature. It's really dangerous temperatures, like 450 degrees. But so we will preheat the board from the back. Because we have a solid ground plane, and that absorbs much of the heat. Then we can continue from the top. Basically heat up surrounding and wiggle the component a bit until it self-aligns into the middle. Okay, that should be enough. Let me turn this off. Now we take some Q-tips and start cleaning up the board. We'll start with the colder section, which is the MCU. As you can see, when we remove the flux, it becomes more shinier and easy to spot if there are any shorts, but luckily there are not, by the looks of it. And we'll also clean up the RF switch. Get some more IPA. Some people would spray the alcohol directly on the board. It's not a good idea, especially if there are sensors like a temperature humidity sensor, because the sensor's sensitive part will get contaminated and the sensor readings will not be precise anymore. So let's clean it up, give it a nice clean. Yeah, this part is a bit tricky with the Q-tips, so we're going to use a brush instead. Also have to wear the Esd protection. I see now there are some components are slightly misaligned. We'll check under the microscope and hopefully won't cause any problem. All right, all looks good. And if everything looks good, no obvious shorts or anything, we can start with the power up test. Hopefully there won't be any magic smoke. Very good. So now is the moment of truth. Let me switch the view, and so hopefully everyone can see. I'll also keep the SMD part here, so we're gonna solder it and the shield. Now, okay, let's do the power up test. Very important. To do this test, we're going to use a OT arc, and we will do a current limiting, and we'll supply it with 3 volts. With the power up test, it's always good to limit the current to somewhere around maybe 80 milliamp, depending on your board's power consumption. You can estimate that by the consumption of the regulator and the microcontroller. In our case, in idle mode, it's around 5 to 10 milliamps, and if it's in transmit mode, it can go up to 60 milliamps. So if we supply between 60 and 100, should be fine. It's just that we need to supply a bit more because of the inrush currents of those bulk capacitors. Before we power this up, just to make sure everything's good, I will do a continuity test again. So between VCC and ground. and V in and ground. So it all looks good. Sometimes might be too good to be true, but we will see. So I'm gonna attach this one to OT arc with the JST adapter. There is no flash in it, so it won't do anything, but we will see the power consumption. So let's head to the laptop. So we do the OT, open the OT app. Start a new project, a power supply project. We set it to 3 volts, 100 milliamps. So 100 M is small m. And we do a current limit, not current cutoff. Digital voltage level is actually 2.8 volts. And we can say OK. Make it full screen. We will start the measurement or start the recording. As you can see, right now the device is not powered up yet. So the moment I say turn on the power supply, okay, now is a moment of truth. Hopefully no shorts, nothing, fingers crossed. Let's go. Okay, it looks like it's doing something. There are no shorts, but it's doing a reset. So this is a reset from the buck boost converter. So it's trying to turn on. That's a usual case I've experienced. It's trying to turn on, but it detects that something is wrong and it just turns back off. So we can zoom it in. We can stop it and then it's really hard without hands. Okay. Okay. Yeah. Now it's clear, but the average power consumption is around 300 microamps. Okay. There's even a audible sound. I'm not sure if you can hear it. So I'll bring it close to the microphone. It's actually the ceramic capacitors that are making those noise. So that means the buck boost converter, which is this one, 1 or 2 pins is not properly soldered, and we have to reflow that as well. So let's do that also. We moved it up a bit. Very nice. Okay, let's give it a try. We will apply some flux. Then use a hot air gun. It's also warm up from behind. Let's go to top. Okay, we wiggled it a little bit. Hopefully that will solve the issue. If not, we have to desolder it, clear the pads, and solder back again. Now we wait until it cools down a bit, then we will power it up and test it again. Clean up some flux residue. Just to make sure that the board itself functions, what we can do, we can bypass the buck boost regulator and power the board directly with 2.8 volts. So that means we basically apply power to the VCC and ground pins here. But first, let's see if the reflow helped us. Start a new measurement. No, it didn't. But the inrush current has reduced. Okay. We stop. We turn off the power. So what I'm going to do, I just supply directly with the 3 volts to the VCC and ground pin to see if it works actually. Okay, grab my adapter leads. I'm gonna remove this one. Actually, we don't need it. Oh. So, a small jumper cable, connect to ground and VCC. All right. Then we connect ground to ground and VCC to VCC. Okay, we're gonna apply power. I think I've stopped measurement. Wait, let's start new recording. Delete this one. Apply power. Okay. Is idling at around 45 milliamps. Now, what we can do, we can try to reflash it and then see if we can read the ID of the microcontroller or make it to do something. Right, in order to reflash the board, we are going to use a ST-Link. Actually, so we have two versions of the ST-Link, both of which could be used. One is the ST-Link V3 set, and the other one is ST-Link V3 Mini. And I made a small adapter board for it. I'm going to actually use the Mini version. So, adapter board plugs here. And then this goes to a USB port. And on the laptop, it opens as a flash drive. And let's actually try to write something to it. And so I have a couple of pre-built binaries, like the basic test and power down test. So let's do the basic test first. And let me bring up the OT arc. You can see there was a reset happening here. So if I flash the board with the basic test, you can see the power consumption going down. The board comes back up. Let's see how it looks. Let's open the terminal. And connect to this. I believe it's COM4. Nothing, okay. Let's try the power stop. Still consuming high current. So I think we need to properly rework the buck boost converter. Interesting. Right. Yeah, as you can see, when I flash the... So the power consumption doesn't go down. Let's try the Cube Programmer. STM32 Cube Programmer. See if we can read the ID of the chip. Alright, chip ID read is successful. Target device STM32WL, that is a good news. So, but we need to solve the issue with the buck boost converter, because I'm suspecting that is the main culprit here. It's consuming way too much current. So I'm gonna disconnect that and change the view. Okay, we know that our microcontroller works, it is functional, but our buck boost converter, it's not. So let's repeat our reflow process. This time I'm going to remove the buck boost converter completely off board and see which pin is not connected, or are there any shorts or things like that. Okay, let's carefully remove it. Very good. Now we can inspect it under the microscope. So what we did, basically remove the buck boost converter, and you can see some of the pads are completely clean, which means they were not making contact. And we will be able to see better if I clean it up. So let me just real quick clean this up. So there we go. So some pads are Basically, there are not enough solder in them. That's the problem with the BGA soldering. It's really hard to get it right manually. You need a really precise picking and placing and optical alignment. So what we're gonna do, we're gonna clean up those pads and solder a new part in. Hopefully that will solve the issue. So let's do that. In order to do the cleanup, we need a solder wick. So there we go. I'm going to use this solder wick, which is really nice for this kind of work because it's a narrow one. Apply a bit of a flux to help with the absorption process. Actually, what we exactly need to do is to do a reballing, kind of reballing. So basically align all the pads at the tip of the soldering iron. Then make sure that each pad has the same amount of solder. Let's do that under the microscope. Okay. Then we clean up and inspect. This is good enough. Now we're gonna apply a bit of solder. Okay. Now we're gonna apply a bit of a solder flux and bring a new component. Actually, we can use the same component, but it's better if it has a clean pad. Let me do that real quick. So these are the parts. And a cut tape. I'm just gonna remove one more. Okay. Align the pin mark. Oops. Let me realign it. Okay, now we're gonna do the hot air reflow. It's really hard to do it under the camera. Looks aligned, but let's see if it's actually all the contacts are intact. So we're gonna wait a bit till it cools down. Okay, conductivity test passed. Now let's power this up. So this time I'm attaching the OT arc power supply to the V in and ground. So that's our ground, that's our V in. And let's switch to the laptop. Create new power supply. Let's do 200. Okay, start recording. Apply power. The same issue. Looks like this is gonna haunt us. Okay, let's turn it back off until we get it right. One more round of reflow. Okay, I'm gonna move the camera a bit because it gets in the way. We're gonna fiddle around until we make it right. Let's clean this up. Okay, let's start a new recording and apply power. The same problem. Okay. There is no stopping until we fix the issue. So let's disable it. All right, one more round. That is why I hate BGA parts. So let's remove this. In the actual production, when we got some faulty units, it was always the buck boost converter, because the pitch size is too small. I believe it's around 0.4 millimeters, and that's why that's the main component which reduces the yield. So in the next revision, we will actually consider using a different package of the same part. So we contacted a company behind it, Ricoh, the Japanese company, and they agreed to manufacture this with a different package. I believe it's called the DFN package, and that will increase the yield quite significantly, because as you can see, the pitch size is really small, and it's increases the manufacturing cost a bit because of that. But as of now, this was the only package size available at 2.8 volts output. That's why we've been forced to use it. So let's clean the pads up. Looks good. Let me check under the microscope. So let's clean more. There we go. All right, that looks better. Now we applied flux. We can technically use the same part, but just to make sure we have nice and those solder balls. Not sure if it's visible, but I'm gonna use a new one. Let me make sure the alignment is good. It's not, we have to rotate it. There we go. Now we place. And then reflow. All right, let's hope that that will fix the issue. Okay, it looks like a war zone, but at least the alignment is good. All right, oh God, I hate BGA parts. So, okay, it is what it is. Let's clean this up. Actually, let me also quickly double check the surrounding parts because there might be some shorts. No, looks good. Okay, let's power this up. Sometimes it's actually could be that the high impedance source is causing it. So let's try with this one first. Sorry about the noise. Start. Okay, it's resetting. Let's what I'm gonna do also. Let me stop this. Test with the batteries. So we have here a generic node with a battery built in. So I'm going to use that. So I have a here a pull tab, and probably you can also hear the clicks. Yeah, it's the same problem. So, one more round. Hope you are enjoying this. If this doesn't solve the issue, then we're gonna go ballistic. Let's see how it goes. Clean it up, looks good. All right, let's start. Wait, let me turn this off and start. Okay, that looks good. Now let's see if the buck boost converter is actually running. That means we have to measure 2.8 volts at the output. And that pin is these two, so the VCC and ground pins, which are here. So let's change this. Nothing. It's consuming 2.8 microamps. VCC and ground. In is 3 volts. With no voltage output. Okay. Looks like enable pin is not connected. So that means another session for reflow. Let's keep the ballistic approach to the end. I'm gonna put it here because it's more stable. I should also check the live chat. So, our tiny little chip seems like turns on. Where did it go? Tiny little chip here. Yeah, some balls are missing. Hope you can see. Yeah, we're gonna have to reball this later. That was the third chip we have destroyed. We still have two more. But now that the chip is removed, I just want to quickly measure the power consumption of the microcontroller. Come on, get in. Oh, come on. Pin header is really hard to work with. Okay. Gonna need a new jumper cable. Here we go. So VCC and ground. Okay, it's doing something. that's when I press the reset button. So the MCU is active, is actually functional. The problem is the buck boost converter. So this is the last try of soldering the buck boost converter man versus the BGA package. Apply a bit of solder. Check with the microscope. Okay, looks good. Right, replace the component, now we solder it. And we have to keep it aligned, otherwise it just moves around as the solder and flux melts. So hopefully that alignment will help. Right, our precious little buck boost converter. Gonna let it cool down a bit. And in the meantime, change the connector. See the alignment. No, it's slightly misaligned. So we can check it under the microscope. But let's try. Open the OT. Start new recording and the same problem. Okay, I'm just gonna try align it, and if that doesn't work, we'll have a different approach. Okay. Looks good enough. So, okay, alignment looks good. I'm gonna open the OT again. Let's create a new measurement. Let's follow the graph. Right, new recording. Okay, then that means this is not gonna work. What we are going to do is the ballistic approach. No, I'm just kidding. But we're gonna bypass the buck boost converter. And I'm gonna show you something interesting. First, let's remove the buck boost. And then clean up the pads. Now let's try to power this up directly. So VCC and the ground. Good. We also attach our Esd link. This pin connector doesn't really work well with the standard pin headers. Oh, okay, it's bent a little bit. All right, and then we plug in the Esd link. Okay, device is visible, and okay, and we're also going to open the serial terminal, COM4 115 to 100, and open our test binaries, and let's flash it. Yeah, success. So it's starting the test, and we can see, okay, it's now gonna play the buzzer. and you can see RGB LEDs blinking. So the rest of the board is functional, except the buck-boost converter was troublesome, which we couldn't get it right under these circumstances. But that's okay, because we have a plan B. And well, that is a success on its own. We have a running system. And now let's flash it with the Lorawan application, see if it can transmit the data. And for that, we have the workspace view. All right, sorry for the technical difficulty. So I think that's where we were left. As we can see, we have a running system. It's doing the infinite loop of RGB LED blink. But what we are going to do is now, let's switch to laptop. Okay, as you can see, it's showing the energy consumption around 8 and 10 milliamps, depending on the LED color. So what we're gonna do, just gonna close this up for now. And here we can see all the tests that have been passed. So it failed to read the secure element. It's probably some pin connection, but it erased the flash. That is good. And we also heard the buzzer. That is also good. And yeah. Now let's try to send a Lorawan packet, at least. So we have a device created here, and if we flash it with a new binary, it should actually join the network and start sending some data. So let me plug this in. Okay, and also make sure that this one is connected as well. Okay. Let's give it a go. I'm not sure if it's gonna work, but gonna burn this binary. Okay, it's trying. So it's read the sensors, but it's failing to join. Interesting. I hope there are gateways nearby. E. Okay. Okay, let's see what's going on. Gonna disconnect this and also just visually inspect the RF path. Maybe some component is not properly soldered. Most probably it will come down to the RF switch, which is the usual suspect. But other than that, yeah, everything else looks fine. So let's give it a try. So let's see. Now the RF switch is removed. I added a bit of a tab of solder just to make sure there's enough. And then we're gonna resolder it back. And make sure we have some flux here. All right. Let's put it back on. Need another one. Okay, that's good. All right, that is soldered. And we need to bypass the back boost converter. So what I'm doing basically is to bypass the buck boost converter and connect its input to the output directly. So I'm going to use a small jumper wire and from the input caps it's not really add a bit more flux. There we go. And that will be connected to the output. There we go. We jumped it across, and hopefully that will help us to directly tap into the VCC line. Now let's use this plug instead, and then plug this in straight to the power source. So now let's do a laptop view. I'm gonna start the power and see if it's doing any transmissions. Looks like it doesn't, unfortunately. Okay, let's switch to the laptop view and have a look. Maybe we missed something. So it's not that clean. We need to clean it up a bit more. Alright, so we did the rework of the RF switch. Should be soldered now. Unfortunately, I don't have a spectrum analyzer, so we could see whether it's actually transmitting any RF signal or not. But by the looks of it, the RF switch is aligned nicely and the solder joint seems to be intact. No shorts, nothing. All the other parts seems to be okay. Let's do a bit more cleanup of the pins because there's a solder flux residue left all over, even though it's a no clean solder paste. Or simply could mean that we misplaced one component. So let's see, it all looks good. our bodge, bypassing looks like there's a bit of a cold solder joint. I'm gonna fix that one. Alright, and we might as well solder the power button as we promised. So oh, sorry, it's not the power button, it's the push button. So user push button. And the other side. There we go. All right. No, still nothing. Looks by the looks of it. Maybe I have the wrong image. Just let me double check that. Okay, we need to reset. Perfect. And it measured the temperature and humidity sensor. Okay, that looks good. but also let's test the low power. Let's track this. Okay, went down. Power went down, that is good. It's 1.4 milliamp, so it means it's not going into low power mode. It's not able to go into low power mode. That's probably due to the RTC clock. That's also probably why Lorawan app also fails. Interesting, very interesting. I'm gonna flash this back. So it's partially functional, but not fully, unfortunately. And can visualize this one. So what I wanted to show you actually is I made a slightly hacked version of the generic node. So normally, as I mentioned earlier, we are using 2 AA batteries. Actually, because of the buck boost that we are using on board, it can accept voltages 2.8 or 1.8 up to 5.5 volts, it also says here. And what I did, so thanks to Voltaic Systems, they provided this high efficiency solar panels and made the batteryless version of the generic node. So we can stick this solar panel on the back or in the front, depending on the placement. And here, this board is a AEM LIC. It's from Dutch maker Jasper Sikken, and he makes these boards and he's selling them on Tindy. They have a couple of versions. So I made a couple of versions also, and this is the normal solar powered, and it uses LiPo battery as an energy storage. So I've used a small LiPo battery, and this board is AEM Lion. This one uses a lithium-ion battery or lithium polymer as a storage. But here, this one is more interesting because this one doesn't use battery. It uses a lithium-ion capacitor, and it can hold charge quite some time. This one is a 30 farad, and with some careful programming, and let's say once every hour update rate, we can technically for a very, very long time power this board, power the generic node from this solar panels. So now let's just plug it in. It's been sitting on the window side since the morning, and I hope the lithium-ion capacitor is fully charged, but let's just verify that. And we carefully measure the voltage. That is 3.73, which is almost 95%, because the nominal voltage of the lithium-ion capacitors are 3.8 volts, so it's almost full. That is good. Now, and this board provides output voltage of 2.2 volts, which is good enough for the generic node. Let's plug this in. You can see it starts to blink. Then it will do a bunch of tests. Also buzzer. Probably you can hear. There we go. Now, interesting point we can observe. Only red light blinks. Well, that's because it's now operating directly from 2.2 volts, and 2.2 volt forward voltage is only able to light up the red LED. The other ones are green and blue. It's not enough. But on a normal functional generic node, so this one is partially functional, it's not fully functional, but here we have a fully functional generic node, or I can demonstrate on this one. Another fully functional generic node. If we flash this, let's plug in ST-Link. Okay, let's head to the desktop. Okay, we're gonna need serial terminal. We don't need this now, and we will flash it with this firmware. And let's head to the TTN console. Here we can see we received the join request and join accept, and it's also printing here. For some reason, join also fails here. I don't know why. Maybe okay, let me try one more thing. Alright, yeah, looks like I'm not using the correct binary. That's what happens when you use a precompiled binary. So let's give it a try one more time. I'm gonna reflash this and let's switch to the laptop. Clear, and so basically this generic node is now powered with a indoor light. And that was the test sample, but more interesting application is the Lorawan application. So I'm gonna clear this up and flash it with the latest version of the binary, and then we'll see. Okay, this one joins. Let's see. Okay, let's clear this up. And it's great. It's sending measurement data, battery voltage, humidity, and temperature. Okay, that is good news, which means actually might be that the node that we soldered also is functional. And let's give it a try. So I'm gonna disconnect this and take the node that we soldered today and power it up with the OT so we can see what is going on. Okay, let's plug this in carefully. All right, let's head to the laptop. Now, okay, let's clear everything, also clear the TTN console. Let's go back and flash it with the new firmware. That's what happens when you do live streaming for so long. All right, okay, successfully initialize all sensors. Let's see if it's sending anything. Great. Oh, that is really nice. So RSSI minus 55, that's not bad. And we have temperature and humidity measurements, also good. And the battery voltage, it's not going to be correct because to do the battery voltage measurement, we were using the normal generic node, we are using the buck boost converter, and built in, it has a battery voltage divider or measurement circuit. Right now we don't have that. Now that means this line is just floating. It's gonna change as I touch it or as I move it around. So don't worry about that, but temperature and humidity measurements are accurate and it's really good. That means our board is functional, or 95% functional except the buck boost converter. So right now, what we're gonna do is I'm going to leave this board running with this solar panel that I made. Okay, now, okay, this is how we're gonna install it. Generic node goes here. We put the seal back on. Then we attach the solar power, and just to double check everything works on the TTN console. Okay, it sent another join accept. All right, okay, it is doing the measurements, and now we're going to close this up and leave it running. So these solar panels are really highly efficient, and they can also charge the battery or the lithium-ion capacitor inside, even with the indoor lights. So that really gives us a nice battery or energy harvesting option. It's really good to use. So let's see what's the temperature like. It's 21 degrees. It's a normal room temperature, that's fine. Let's move it outside. So I'm taking the sensor and putting it outside. Sorry for the noise. And let's see if the temperature measurements are changing, or how fast it's going to change. So the update rate is every 10 seconds. Let's see what's the outside temperature in Amsterdam. going to take a while because it's located, the sensors are inside the enclosure, and there's a bit of a time offset until the measurements are accurate. But sooner or later we're going to see a temperature drop. Let me just close the windows because it's getting cold here. Slight drop now. We actually did a measurement that what is the delay. It was a couple of minutes with the units that we measured. As you can see, it's slowly going down, and it's going to take a while to equalize with the outdoor temperatures, and we don't have that much time. But it's good to see that, okay, it's now 20. Yeah, it's not super responsive, but we can see the drop. Okay, it's 19.8, and humidity also increased a bit. Yeah, 19.3. You got the point. I'm gonna take it back. Just gonna leave it in the office for the rest of the day. All right, it's been a long day, and we did almost functional, like almost fully functional generic node. We soldered everything. We went through the double-sided soldering process, how we do it at home with the basic tools like this. And yeah, we did the basic test. Most of the sensors are functional, and except the secure element, we couldn't read it, but that's a debug session for some other time. And then we also demonstrated the hacked version of the generic node, which was not using a typical batteries, but it's using a small indoor capable solar panel with a lithium-ion capacitor, and basically shows that I actually ran it for 24 hours with a fully charged lithium-ion capacitor with 30 farad, and the voltage with only the indoor lights overnight and no lights on, just maybe 7 or 8 hours of indoor light, and the voltage of the lithium-ion capacitor dropped from 3.8 down to 3.6. So which means with a normal daylight or with a bit of a stronger indoor light, this can definitely be used as a battery-less option. And with the careful programming and with slower update rates of, let's say, 1 packet every hour, basically this device can last for many, many years until some of the components are failing. But other than that, there won't be any need to recharge the battery or change the battery at all. I hope you liked the session. So you can contact me on Twitter. My handle is at AzeriMaker, and you can also write to our the Things Network page. Just they will forward messages to me. If you have any question, I will be more than happy to answer. You can also head to our GitHub page, and if you have any specific question, just open a new issue and we will address it there. We also have a forum, the Things Network forum, and we also have a dedicated section over there for the generic node. So that's also another option to ask questions or learn more about the generic node. Okay, thanks everyone for tuning in. I hope you liked it. We'll make a condensed version of the session, and that will we'll try to make it more informative and let's say much shorter, 20 minutes, 30 minutes max, not 8 hours, which has been right now 6, but with some preparation work, it's more than 8 hours now. Okay, it's late at night already. Okay, thanks everyone for tuning in, and hope to see you or virtually, maybe also physically, in another Things conference. Bye.